Today, I'm going to talk about a study we have done to estimate the effects of weather on brain function using functional MRI. We used AI as a tool to study this, but ultimately, this is a story about how AI takes, quote, shortcuts. So what are shortcuts? In machine learning, a model will sometimes find signals that have nothing to do with what we are actually interested in. For example, in a classic computer vision study, an AI was trained to classify huskies versus wolves. It achieved high accuracy, but when researchers looked closer, the AI wasn't looking at the animal at all, it was looking at the background. It had simply learned to classify snow. Another example is skin cancer detection. Studies showed some models were actually basing their predictions on the rulers placed next to the tumors to indicate size, rather than the pathology of the cancer itself. Keep this in mind as we look at our MRI data. So why look at the weather? As you likely know from personal experience, the weather and changing seasons can affect our cognitive functions and our mood. Studies support this. Cognitive performance often shows a summer dip in August, and our moods fluctuate, leading to conditions like seasonal affective disorder in the winter. On a macro level, even the stock market correlates with the weather, likely because individual traders' moods and confidence are collectively driving fluctuations in market prices. To really understand what's happening, we have to look at the brain. If environmental factors are affecting our cognition, those effects must be mediated by the brain. We turned to MRI, scanning the same individuals over a long period of time. We used various functional measures to indicate brain activity, such as REHO, ALFF, and functional connectivity matrices, and paired them with weather parameters like temperature and daylight length. Instead of asking, does the weather change the brain, we asked the AI the reverse. Can you look at this brain data and tell me what the weather is outside? If it can, it suggests the weather left a measurable footprint on the brain. First, we looked at using functional measures to predict the weather parameters. As you can see here, it was quite successful. Brain activity and connectivity measures could successfully predict daylight length and temperature. At first glance, this was consistent with our hypothesis. But as scientists, we needed to be more rigorous. We wanted to see if other measures, ones that are highly unlikely to change on a daily basis, could also predict the weather. If they could, that would be a major red flag. So we turned to anatomical data. Logically, the physical infrastructure of the brain shouldn't vary significantly on a daily basis due to the weather. Yet we found that our predictive accuracy was actually much higher using structural data, and we could predict even more weather parameters. Because structural data generally has a higher quality than functional data, it suggested the model might just be picking up on the MRI signal itself. To test this, we looked at areas completely outside the brain. We wanted to see if regions consisting of just empty air in the scanner could still predict the weather. Surprisingly, they could. The predictive accuracy for daylight length was still statistically significant at 0.47. This strongly suggested that the predictions weren't based on human brain activity at all. To definitively prove this, we looked at our phantom data. A phantom is a calibration device scanned daily to test the stability of the MRI scanner. When we looked at the signals inside the phantom, they were negatively correlated with daylight length. Furthermore, if we built a machine learning model to predict daylight length using only the phantom data, the prediction accuracy jumped to 0.7. This conclusively told us that the signals the AI was finding were machine artifacts. Just to recap, we found that we can accurately predict weather effects like daylight length and temperature from MRI data. However, this is not due to real brain activity. MRI scanners are highly complex machines with sensitive superconducting and cooling systems. These systems, along with the stability of the electrical power supply, vary across different seasons and directly affect the signals the scanner picks up. Which brings me to my final point, a cautionary note. As the quote goes, "With great power comes great responsibility." Machine learning is an incredibly powerful tool in neuroscience, but it is fundamentally a pattern-matching algorithm. It doesn't understand biology. If there is a hidden artifact in your data, the AI will find it and exploit it. We must thoroughly validate our models and always check careful control conditions before drawing biological conclusions. Lastly, I would like to thank all of our collaborators and the creators of the open access datasets that made this study possible. Thank you very much.